Hello, my name's Gary Pace. Here's another YouTube on Weld Defects. This is project started out with me going to take a Nuclear Regulatory Commission course and put it online, go through their slides. Anyways, this one's on distortion. I was going to do weld defects, but then it turned into me chopping it up into a lot of different ones. So we're going to talk about weld defects in this one, particularly distortion. As you guys know, I'm like the king of chopping up other people's work. One of my superpowers, I guess, is being able to find non-copyright material in regards to welding on the internet. Nuclear Regulatory Commission, Can Teach, which is Can Do, the nuclear technology people from Canadian deuterium, uranium projects up there. They got a nice repository. Boilermaker One in Chief. It's an old welding manual for Boilermakers. The rate doesn't even exist in the U.S. Navy anymore. But a lot of really great material. I'm poaching the heck out of that stuff. Steelworker 3 and 2. It's a U.S. Navy course. I think I'm going to steal some stuff out of Machinery Repairman 3 and 2, and also Hull Technician 3 and 2. So any of you out there that want some good information on a budget, this stuff's pretty solid. It's good for most welding processes, and it'll give you the concepts. So a lot of the material that I'm using, it came from there. I poached it. I just might have added my own little bent on it, but that's where I got most of my stuff. I've kind of coalesced it into what you're going to see here. Wanted to throw on another acknowledgement where I borrowed some material, or I guess I'm going to cite it. Numerical simulation of residual stress and strain behavior after temperature modification. And I'm going to butcher these guys' name, and I'm so sorry. Farag Soul and Nada Hamdi. It's in the book Welding Processes, edited by Radovan Kovacic, I think, Southern Methodist University, United States of America. There's the ISBN, and there's the website where you can go to the book. The book is an open source book, open access, peer reviewed. You can poach anything out of it you want as long as you cite what you have poached or borrowed or cited or learned from them. So I haven't had a chance to completely review the book, but it's out there if anybody's more interested. Another good source of material for expanding your knowledge base on welding. Definitions. Discontinuity and defect. What is the difference? Discontinuity is defined as an interruption in the normal physical structure of a weld. A defect is when any discontinuity is of such magnitude that it may impair the normal function of the weldment. It is considered a defect. So all defects are discontinuities, but not all discontinuities are defects. So in a weld or weldment, you might have something that is a blemish. It doesn't seem right. It is a discontinuity. It is an interruption in the normal physical structure of the weld. But it doesn't mean it's going to be of enough magnitude that it'll cause a problem for the weldment. So you can have a discontinuity that's not a defect, but all defects are discontinuities. A little vocabulary bookkeeping that needs to be done there. Introduction into your vocabulary. Discontinuity versus defect. Fusion weld discontinuities. Fusion weld discontinuities are interruptions of the typical structure of a weldment, such as a lack of homogeneity in the mechanical, metallurgical, or physical characteristics of the material or weldment. Discontinuities which exceed recognized acceptance standards are termed defects, a word which signifies rejectability. Fusion weld discontinuities may be classified into three major groups, namely process and procedures related, metallurgical related, and design related. Some discontinuities are related to specific welding processes, while others are related to particular base or filler metals. Discontinuities may be found in the weld metal, the heat affected zone, and the base metal. So what's this mean? We got three different ways we can get a fusion weld discontinuity. Process and procedure related. For example, you're not going to get a slag inclusion on gas tungsten arc welding, or you shouldn't, because you shouldn't be using a slag in general, or a flux. Or you shouldn't have a tungsten inclusion in gas metal arc welding. There's no tungsten. Where did this tungsten magically come from? So certain processes have welding related discontinuities that are, inherent in that process and that process alone. Metallurgical. Sometimes you just get some bad steel. I'm not going to single out, suppliers, but, sometimes certain steel mills will give you less than good steel. So you got to work with some steel you're dealing with. Or, certain materials are going to have different discontinuities than other materials. Aluminum's going to have inherent problems that are different than steel or titanium or other metals. Design related. Sometimes the designer just gets it wrong, and you're going to have to fight that design trying to produce a reasonable part. So sometimes design is just going to kill you. Some discontinuities, like I said, different specific welding processes, base metals or filler metals. Sometimes you get a bad batch of filler material. The guy in purchasing gets a really good deal on some cheap filler material, and you're stuck with it. So you might be fighting that, or you might just have to chuck it. I've had to chuck whole pallets full of flux cord wire. Something was wrong with the stuff. Just that heat batch lot number was just bad. So you got to pitch it. Do your due diligence before you start throwing the money away. But, I've had to do that in the past. Discontinuities, once again, they can be in the weld metal, heat affected zone, and base metal. Today we're going to talk about warpage and distortion, which is more in the base metal. It's not really a weld metal defect per se, but it is a discontinuity that can cause you all kinds of problems. Weld defects, like the welds themselves, must be described in standard terms. Common weld defects that you should be familiar with include incomplete fusion, inadequate joint and root penetration, spatter, overlap, undercut, root cracks, toe cracks, crater cracks, underbead cracks, voids, and inclusions. And we'll throw distortion in here. I'm going to come back and hit the rest of these in a follow-up YouTube video. We'll talk about, spatter, overlap, undercut, root cracks. I've already talked about, cracking. That one's already out there, so we'll talk about voids, inclusions, and everything other than cracking and distortion in upcoming episodes. Definition of a defect. The definition of a defect must be considered in the context of the service conditions to be imposed on the weldment. If the service conditions are not severe, then most discontinuities can be of considerable magnitude and number without jeopardizing the integrity of the weldment. But if the service conditions are severe, then obviously most discontinuities must be considered as defects. So what's this telling us? This is telling us that it depends on what you're doing, what you're making, what your end product is. The boiler and pressure vessel codes, ASME section or B31.1, B31.3, section 1, which is boilers, B31.1, which is power piping, and 31.3, which is process piping. Those have different inspection criteria than, let's say, AWS D1.1 structural steel. And for structural steel, you have different criteria for static loading or cyclical loading. AWS D1.1 is different than D1.5, which is the bridge welding code, because there's a whole host of other different problems that come with bridges, the cyclical loading, wind loading. I don't even know half of the stuff that goes on in the bridge welding code. But what I'm trying to get at is all defects, if it's a rejectable defect in one code, doesn't mean that it's necessarily a defect in another code. It might just be a discontinuity. AWS D1.1 allows quite a bit more porosity than other codes because you're not holding anything under pressure. It's just a structural component. Somebody decided, okay, you can have this much porosity in the welds and not have an issue. So that's the way things kind of work out. So if you got to be sure that you're playing to the same code book when you're talking about defects. Look at your inspection criteria, what the engineer wants, what the inspection criteria is laid down contractually. All these things come into play when you're talking about defects and whether it is a defect for that specific job in that specific situation. List of weld defects. Okay, here I tell welders this and upcoming welding engineers. Probably one of the most important things you really need to learn in regards to the welding trade, industry, whatever, is list of weld defects, because these are things you generally don't want in your welds. So arc strike, inadequate joint penetration, incomplete fusion, porosity, slag inclusions, undercut, cracks of all the different flavors there, spatter, root concavity, excessive reinforcement, which is also known as drop through, overlap, which can be also known as cold lap, appearance, and distortion. These 13 things pretty much cover most of the bad things that can happen in welding and most of the things that you are trying to prevent from happening in welding. So it's a good idea to have these specific, words and terms in your vernacular, your vocabulary, part of your toolkit, so that when you're talking to other people, you can explain what is wrong in a somewhat educated and dignified manner without saying, trying to describe porosity as the bubbly stuff or something, Oh, we've got linear porosity. We've got this type of porosity. Oh, we've got slag inclusions. We've got undercut. We've got cracks. So you can see how important this is. It's, this is the basic building blocks of, welding engineering and welding. These are the bad things that you are trying to either fix or prevent from happening. Can't place enough emphasis on this list. The process of welding involves sudden and non-uniformity, localized heating to high temperatures with somewhat slower cooling. The results are unbalanced residual stresses and distortion. In thinner members, the distortion can be of considerable magnitude to the extent that the weldment may be unusable. In thicker members, under dynamic loading, the residual stresses, which may not have been visually evidenced by distortion, may ultimately cause failure of the weld. So what's that telling us? That's telling us that if we have thinner materials, and I'm going to throw out a number here. I'm not exactly sure where the, thin and thick borderline is. Maybe it's kind of a zone there. But I'm going to say, let's call it 3/8 of an inch, 10 millimeters. 10 millimeters, 3/8 of an inch, and I don't even know if those two are equal. Sorry if my math isn't great on that one. Between those two numbers, and thinner, the material is going to buckle, and you're going to probably be able to see the problems with the buckling and whether or not the distortion is making that part usable or unusable. So that's one side. Thicker members, let's say we're welding some kind of big bridge member, some kind of beam that's 3 inches thick or whatever, some really thick piece of material, and it's under a dynamic load, flexing and twisting and torsion and all these different forces that are cyclical, and dynamic, moving. These residual stresses, you might not have seen them because the part was so thick that it didn't, really distort that you could see it with the visual eye. But there's stresses introduced into that part from all that welding and all that localized heating and cooling that you could have problems later on. It might be a week, it might be 6 weeks, it might be 3 years down the road, but you could have failure of a weld that looks perfectly acceptable from a dimensional standpoint, there wasn't a lot of distortion, but you've got failure later on because there's these stresses built into the part that didn't get taken care of. So distortion, there's a lot of money that goes into dealing with distortion, shipyards, heavy construction, all kinds of different, welding and materials joining situations where distortion is really important. So you really need to keep an eye on distortion. Here you can see bending distortion in welded sheet steel. Here's a warship. I don't know which, I can't see a flag on it, and I don't know which country it is. But anyways, this was taken from numerical simulation of residual stress and strain behavior after temperature modification by Farag Soul and Nada Hamdi. Hope I pronounced the names right if those gentlemen or ladies or individuals are listening to this. Anyways, I'm apologizing, but I'm borrowing your picture and citing it. You can see the distortion and kind of pulls these thin plates together and kind of makes it look like it's a potato chip kind of wavy texture where each weld is or piece of sheet is welded to a strong back. And I probably messed up that lingo. My Navy lingo is from back in the day. I was a boiler operator, so ship's hull parts I'm not real good with. But you can see there's distortion. A lot of people spend a lot of money trying to conquer the problem of bending distortion in welded sheet metal and other types of metal. So here's another example of what can happen when you weld thin materials. Most of the welding processes involve heat. High temperature heat is responsible for much of the welding warpages and stresses that occur during welding operations. When metal is heated, it expands in all directions. When metal cools, it contracts in all directions. Some distortions caused by weld shrinkage are shown in figure 6.42. 42. You can have your, if you're making like a fillet weld there on the top, you can have, your vertical work pulled off center. You can have your flat work pulled out of line. It'll curl up like that, like in the middle, groove weld there. And you can have flat work drawn into a curve. Or if you're making a groove weld, let's say an open root groove weld, you need to be cognizant that that's going to pull together. So when pipe fitters will fit something up to make an open groove weld, they'll space it wider at the far end, the end they're not going to be welding on. They're going to tack it wider there, give it a bigger space because it's going to pull together as they weld. It's going to kind of stitch itself together, draw itself to a close. So, this dimensional distortion thing you need to keep track of. Like, I used to work for a company that made man lifts back in the day, and we had a lot of issues in regards to, we'd have a lot of really long, thin pieces of material that we were welding to make the booms. And, the process we used, we'd have a lot of distortion. We'd have the flat work drawn into a curve and flat work pulled out of line. We had all kinds of issues. And we found a couple of workarounds to make our product, a lot better. So, and usable. So, dimensional distortion, you can't blow it off. You got to think about it and put it into planning when you're making weldments. Dimensional distortion. There is a direct relationship between the amount of temperature change and change in dimension. This is based on the coefficient of thermal expansion. Thermal expansion is a measure of linear increase in unit length based on the change in temperature of the material. The coefficient of expansion is different for the various metals. Aluminum has one of the highest coefficient of expansion ratios and changes in dimension almost twice as much as steel for the same temperature change. So this is telling us you got to worry about what metal you're welding to. Stainless steel is notorious for distortion compared with carbon steel. If you're working with aluminum or titanium, they're going to be different. So you need to, if you're going to be welding different materials, you need to realize that there are, differences from metal to metal, and that's due to, the coefficient of thermal expansion. It's how much a metal or a material is going to grow in length due to the increase in heat. So you need to really keep this in mind. You know, the materials you're using, and then, you know, from history and kind of a general calculation, how much is it expected to grow when you heat it to a certain temperature. This slide I poached from the NRC, but you can see the reference, Welding Handbook, Volume 1, AWS 1991. Fundamentals types of weld distortion. You can get transverse shrinkage, where the part shrinks from side to side. That's A. Longitudinal shrinkage, you know, that's lengthwise the part will shrink. Angular change, okay, you've welded it. Now the angles on everything have twisted and torqued, and it's not what you were thinking you were going to get. Longitudinal bending, you can see that fillet weld. When it pulled, when you had the shrinkage, it pulled it and it caused warpage there, bending. Rotation distortion, that's what I was talking about before, where, you know, if you're welding an open groove weld, you might have to pull it when you tack it on the one end, on the far end from where you're starting to weld. You might have to, you know, throw a little bit of extra space in there, a little bit of extra distance, because that's going to suck up and tighten up on you, and you're going to have problems. And then you've got buckling distortion. This is one I dealt with in one of my previous lives. We did some, what was it, thermal pre-tensioning. We'd heat up the part a couple hundred degrees before we welded it, right before we welded it, and then we'd weld it, and then the part would shrink back to the to its size that it was originally supposed to, the size we were looking at. So buckling distortion. The U.S. Navy worries about this a lot on ships. You know, they're welding a lot of thin materials and long sections, and, you know, ship makers in general. So, and then when the weld cools, it pulls, and you have this buckling distortion. It looks like waves in the metal. This is a phenomenon that generally occurs only in, you know, thinner materials. You're not going to have it with 3-inch plate. It's 3/8 and under generally, I'm thinking. Don't hold me to the 3/8, but I know 1/8 inch you can get this pretty easily. Residual stresses from welding. This is a photo I chopped out of an old military manual. I can't remember which one. There's about a dozen of them. But residual stresses from welding, you can see that we've got longitudinal and transverse shrinkage stresses in a butt weld. So the weld is being pulled together side to side in a transverse manner, and also longitudinally, you know, end to end is in the lengthwise dimension of that weld. So longitudinal, transverse shrinkage in butt welds. Here's distortion in a butt weld where things have pulled and twisted and warped. Anybody that's ever, you know, had a welding class, you know, your basic welding class, and you're doing a pad of beads where you're just welding on the same piece of plate over and over and over, you'll notice that it'll pull like this. It'll turn it, if you're just welding from one side, it'll kind of turn it into a potato chip. You know, kind of give it a potato chip kind of, I don't know, contour. You know, it goes from flat to being kind of dish shaped because you've put in all these residual stresses into these welds. And I guess the example I just said isn't necessarily a butt weld, but like I said, if you have a test plate like this, you can basically turn it into a potato chip kind of shape due to the distortion in the longitudinal and the transverse direction. Here's another example of, you know, shrinkage in butt welds. You know, you start out with one length and then it shrinks down, and it also, you know, affects your width. You know, transverse direction, you start with one dimension and then you end up with another dimension. So these are things that you, once again, you need to be cognizant of. So, and plus, I'm just going to tell you, I see a picture in one of these old military manuals or the Nuclear Regulatory Commission. it's going in the slideshow. So kind of give you a couple of different variants of the same thing. Residual stresses from welding, again, longitudinal and transverse shrinkage stresses in a fillet weld. So longitudinal and transverse shrinkage stresses aren't just a phenomena that are associated with groove welds. You can have them in fillet welds. And as fillet welds are probably the most common type of weld, it's something you really need to worry about because it can pull things off, cause warpage, and introduce stresses into a part that you might not want introduced in there. Here's another example of some residual stresses or some distortion in a fillet weld. Same things that can happen. And a lot of it depends on your thickness and, you know, your welding parameters and what you've got going and how well you've got things configured and jigs and fixtures and tacked up to kind of control your distortion. But this is something that can happen. You need to be cognizant of it. Here's some photos showing angular distortion. I don't know if they're photos, drawings. Angular distortion. So you can, you know, have a beam where you'd have some longitudinal bending where you welded something and it'll warp it on you, or pipe. A lot of times really thin-walled pipe, you can get angular distortion or bending. Here they've welded another pipe on. You've got a pipe junction there, and the two pipes coming together, they've welded that 90 on there. Well, that big weld they put in there is going to pull on the other one, so you can end up with, you know, distortion. Pipe fitters deal with this all the time, so a lot of them have, the good ones have really good recognition of what is going to happen and why, and then they'll put some countermeasures into effect to keep it from bending. You know, whether that's, you know, not heating the hell out of it or, you know, trying to minimize the distortion by tacking things and fixturing and, you know, maybe heating it afterwards. There's a number of different tactics that are used to, you know, combat, you know, angular distortion. The effects of thermal properties of stainless steel on welding conditions and distortion. The thermal properties, coefficients of thermal conductivity and expansion, melting point of stainless steel differ a little bit from those of carbon steels. You got a bunch of chromium and nickel in there. It throws off the chemistry and the way that stainless steels, you know, work from a metallurgical standpoint. A lot of stainless steels are austenitic, which means they've got face-centered cubic structure, which makes it a whole different ball game than carbon steels. You know, coefficient of thermal expansion is different. Coefficient of conductivity is different. Everything, thermal conductivity, electrical conductivity, it's all different. So the differences affect welding operation, and steps must be taken to compensate for these effects in thermal and these thermal properties. So you need to keep that in mind. Like I said, stainless steels, I've never really welded them a bunch, but I worked out at the Hanford nuclear site and everything was stainless steel, and we did a lot of really thin wall pipe. And these guys that I knew, some buddies of mine that were pipe fitters, they were constantly fighting distortion with this stainless steel pipe and tubing, just because stainless is really squirrely. Sorry for you guys in India and wherever. Squirrely just means that the material just doesn't behave the way it's supposed to, or you'd think it would. It just kind of has a mind of its own when you're welding it. Preheating to reduce distortion should be avoided when welding austenitic stainless steels. Carbon steels, a lot of times you can preheat them to reduce distortion. You don't do that with austenitic stainless steels. Your 300 grade, your 316, 304, 308, 309, whatever. Austenitic stainless steels, it's bad practice to, you know, use preheat to try and minimize distortion. You know, this could lead to sensitization in portions of the weld. So sensitization is where you strip out the chromium. The chromium ties up with carbon, and then you've got these chromiums that precipitate into the grain boundaries, and then whatever fluid or service condition you have, it'll chew away at that weld in the heat affected zone, and your weld will just fall out. So that's called sensitization of the weld joint, and that's why we don't preheat austenitic stainless steels to, minimize or reduce distortion. Special precautions are required if tack welding is used to control distortion and maintain joint alignment. If these precautions are not taken, tack welds can be a source of weld metal cracking, porosity, incomplete penetration, or lack of fusion. A tack weld must be the same quality as the rest of the weld. It should be inspected to ensure that it is sound and does not contain tiny cracks or porosity. The surface of the tack weld should be ground to a smooth, concave contour so that it will be completely melted into the final weld. So you need to really be careful with, your tack welds if you're doing tack welds as a form of distortion control. They need to be high quality. You can't have just anybody tacking things up and leaving, slag or dirt or whatever you've got in there. Porosity, if you've got that, you need to grind that out and fix it. Incomplete penetration, lack of fusion, those also need to be fixed, because, in a bigger philosophical, discussion, what happens at the bottom of the weld, it'll carry up. So if you got problems in that tack weld in the root, it'll follow you all the way to the top, whether it's cracking, porosity, whatever. It's like building a house with a really bad foundation. You're not going to be able to fix. You put in a foundation that's really bad, nothing's level, it's on a swamp, it doesn't work, it's settling. Your house is going to be crap. You're not going to have the ability to, fix the things that are wrong with the foundation, with your walls, your windows, your doors. Nothing's going to fit. So it all starts with the foundation. And in this case, it's the root of the weld. So you really need to put emphasis on getting that root, and any tacks that might be incorporated into the root passes, that's got to be solid. That's got to be really good quality, because otherwise you're going to chase that all the way to the top of the weld. Sorry, kind of got off on a rant there, but trying to tie a bunch of things together here. So residual stresses and distortion affect materials by contributing to buckling, curling, and fracturing at low applied stress levels. When residual stresses and their accompanying distortion are present, buckling may occur at smaller compressive loads than would be predicted otherwise. In tension, residual stresses may lead to high local stresses in weld regions of low toughness and may result in running brittle cracks, which can spread to low overall stress areas. Residual stresses may also contribute to fatigue or corrosion failures. There's people that spend millions of dollars trying to figure out, how to control residual stresses, distortion, keep cracking and all that from happening. So, something to keep in mind. Minimization of warpage. Warpage can be minimized in smaller structures by different techniques, which include the following: the use of restraining fixtures, strong backs, and mini tack welds, the use of heat sinks or the fast cooling of welds, the pre-distortion or pre-bending of parts prior to welding, balancing welds about the weldament's neutral axis or using wandering sequences or backstep welding, the use of intermittent welding to reduce the volume of weld metal, the use of proper joint design selection and minimum size of weld, and as a last resort, the use of preheat or peening. I'm not going to get into these in this episode, or volume or whatever we're at, chapter. I'm going to take up here in the next week or so and hopefully release one where I talk about how to minimize warpage. So that'll be volume 2. I'll probably take up right here where I left off, and we'll talk about ways to minimize warpage. I'm trying to kind of keep the size of these YouTube videos maybe a little smaller than in previous iterations of the work I put out. So next time we'll talk about the minimization of warpage. We'll talk about how to reduce distortion and what some people have done in regards to that, and I'll give you guys a list of books if you're really hardcore readers, that if you want to dig into this subject matter, there's people that really sharp people that have put together a lot of research on this over the last 50 or 60 years. So I'll try and point you in that direction if you're interested in it. Feedback. You guys know where the button is, the thumbs up or the thumbs down, and where to leave the comments. So you guys have comments you need to leave me, or shoot me an email. My email address is on there. I'll try and answer what questions I can. Pretty much a repeat of the previous slide. There's my address, email, my website. There's a couple of free things on there. You got any questions, comments? Give me a shout.